Sorry for the technical difficulties. So let's just look over this again because the end of the last video got screwed up. So this was the proof I was presenting at the end of the last video. The variance of ax plus b is equal to a squared times the variance of x, right? And so in the proof, I used the definition of variance and the corollary to Theorem 6.4. That corollary says that e of ax plus b is equal to a times e of x plus b. Okay? And so the variance of ax plus b is equal to e of ax plus b minus e of ax plus b, all that in parentheses, squared, right? Because the variance of something is the expectation of that thing minus its minus e of that squared. Okay? So then ax plus b, you can take the a out here, and it's a times ex minus b, and then the b and the minus b cancel, and you get ax minus ae of x here in the bracket. And then you're squaring this, so you can factor out the a squared here, and you get a squared times e of x squared. And so then you can move out the a squared here, and there's a squared times e of x minus e of x squared. And by the definition of variance, e of x minus e of x squared, that's the variance of x. And so this is a squared times the variance of x. So the variance of ax plus b is equal to a squared times the variance of x. Okay? And so that's the proof of Theorem 6.6 right there. Okay, and the homework for section 6.6 is on page 209, exercises 1 and 3. Okay, let's keep going. Okay, so 6.7 is on Chebyshev's inequality. Okay, so Theorem 6.7 is Chebyshev's inequality. Okay, and so it says let capital X be a random variable. If e of x squared is finite, that's what that notation means, then for any c constant c greater than 0, we have that the probability that the absolute value of x is greater or equal to c is less than or equal to e of x squared divided by c squared. We get this inequality. Okay? So less than or equals to. Okay? Okay, so that's Chebyshev's inequality. It's theorem. Corollary to the theorem is let x be a random variable with finite mean mu and finite variance sigma squared. For constants d greater than 0 and k greater than 0, we have that a, the probability that the absolute value of x minus mu is greater or equal to d is less than or equal to mu squared over d squared. And b, the probability that the absolute value of x minus mu is less than k sigma is greater than or equal to 1 minus 1 over k squared. Okay? Okay? This corollary is also referred to as Chebyshev's inequality. Okay? Okay, so okay, example 6.25. When a certain speed control device is set at m miles per hour, the actual speed in miles per hour of an automobile, of a car, I'm just going to say of a car, with this device is a random variable x with mean mu equal to m, little m, and standard deviation sigma, which is equal to 3. If the device is set at 45 miles per hour with a 50 mile per hour speed limit, what is the Chebyshev estimate of the probability that the speed of the automobile will exceed the speed limit? Okay, and so the answer is the following. We're going to assume capital X is a continuous random variable. Okay, so we have that the probability of the actual speed exceeds the speed limit is equal to the probability that x is bigger than 50. Right, so okay, so the actual speed in miles per hour of a car with this device is a random variable x, right? So x is the actual speed. And we're looking for, the question is, what is the Chebyshev estimate of the probability that the speed of the automobile will exceed the speed limit? Okay, so what we want to know is what is the probability, we're looking at the probability that the actual speed exceeds the speed limit. x is the value of the actual speed. And the speed limit is 50 miles per hour, speed limit. So here's the speed limit, it's 50. And so you want the probability of the actual speed exceeds the speed limit, because that's what we're talking about in the question, is equal to the probability that the value of x, which is the actual speed, is greater than 50, which is the speed limit. Okay? That's equal to the probability that x is greater than or equal to 50. That's because x is a continuous random variable, and so the probability of a continuous random variable equaling any fixed number is 0. And so we can include x equals 50 into this inequality, and it will not change the total probability, right? So the probability that x is greater than 50 is equal to the probability that x is greater than, so the probability x is greater than 50 is equal to the probability that x is greater than 50, okay? And then this is less than or equal to the probability that the absolute value of x minus 45 is greater than or equal to 5, okay? Okay, so if we have the values of x, right, and here is 45, right, and if we're looking at a difference of 5, right, a difference of 5 from 45, saying that x minus 45 is greater than or equal to 5, would mean you're looking at these values of x, where x is either less than or equal to 40, or x is greater than or equal to 50, right? Okay? So that would be the probability that the absolute value of x minus 45 is greater than or equal to 5, right? If x is at least 5 away from 45, then it's either less than or equal to 40 or greater than or equal to 50. And so the probability of all those possible x values is greater than or equal to the probability that just x is greater than or equal to 50. Okay? So this probability is only accounting for the probability of these possible values of x. With this inequality here, the probability of this, I'm now adding possible values of x. And so then you'll see, so you see that the probability of this has to be greater than or equal to the probability of that. Because here we're considering all the x's greater than or equal to 50 and additional values of x. And so this must have a more likelihood of happening than that. Okay? And so now this is less than or equal to sigma squared over 5 squared. This is the corollary to Chebyshev's inequality. This is the corollary to Chebyshev's inequality. Okay, so I drew that picture for you before. I'm just going to erase it here because I'm going to need the room. Okay, so that explained this last inequality. Here, by the corollary to Chebyshev's inequality, right, you can say that the probability of the absolute value of x minus mu is greater than or equal to d is less than or equal to sigma squared over d squared. Okay, so we're saying greater than or equal to 5 here. And so that's why there's a 5 there. That's the d there. Okay? So sigma goes there, and then the mu is the mean. Okay, and so 45 is the mean. Okay, and so then this is equal to, well, if sigma is 3 and sigma squared is 9 and 5 squared is 25, so that's equal to 9 over 25. And as a decimal, that's 0.36. Okay, and so the probability of the actual speed exceeding the speed limit is less than or equal to 0.36. That is the Chebyshev estimate of that probability. The Chebyshev estimate of that probability is that the probability that the actual seed exceeds the speed limit is at most less or equal to 0.36. Okay, so we found an upper bound for that probability. Okay, and so the homework for 6.7, so this is 6.7 we're talking about. The homework for this section is pages 211 to 212, and it's going to be exercise number 4. Okay. Okay. In addition, I want you to study table 6.2 on page 213. Okay. So now I'm going to actually erase this other stuff just to write down that additional part of the homework. So I'll rewrite this part of the homework here. Okay, so the homework for 6.7 is, this is for 6.7. The homework is pages 211 to 212, exercise number 4. Okay, and I want you to study table 6.2 on page 213. Okay, so this exercise number 4, page 211 to 212, and study the table 6.2 on page 213. That's the homework for 6.7. Okay. Okay. And okay, so now 6.8. For 6.8, I want to do the means and variances of special probability distributions. Okay, so example 6.26. The probability a person is infected by a certain disease. By a certain disease, I'll just write disease is 0.05. Okay, that's 5%. If 1,000 people are exposed, what is the expected number that will become infected? Except if one of them's Dr. Anthony Fauci, then he won't get infected. So if 1,000 people are exposed, what is the expected number that will become infected? Okay, so let X equal to the number of people infected. X is a binomial random variable. Right? It's a binomial random variable because there's two choices: either someone's infected or not infected, right? Success or failure. So we have X is a binomial random variable with P is equal to 0.05. That's a probability of success. Remember, success is not always a good thing in probability, right? So here, a success is getting the virus, okay? So P, the probability of success getting the virus, is 0.05, and N is equal to 1,000. People, okay? So the number of people is 1,000, that's N is 1,000, and the probability of success getting sick is 5%, 0.05. So E of X is just N times P, which is the number of people exposed times the probability of being infected, and that's 50. Okay, so the expected number of people to become infected is the expected value of that binomial random variable x, which is 50, n times p, 1,000 times 0.05, and you get 50. Okay. Okay, so that's example 6.26, and it's easy. Right? You just know the fact that e of x is n times p. There. So example 6.26. If the distributions of raisins per cookie is a Poisson with lambda equal to 4, what is the expected value? What is the expected number of raisins per cookie? Okay, so if the distribution of raisins per cookie is a Poisson random variable with lambda equal to 4, what is the expected number of raisins per cookie? And so here, right, we're going to let x equal the number of raisins per cookie. Okay, and it's the same Poisson. It's a Poisson random variable with lambda equal to 4. Okay, then e of x is equal to lambda, which is 4. Okay? So if you have a Poisson random variable with a value for lambda, then the expected value is just lambda. E of x is lambda. Alright, so before e of x was n times p for a binomial random variable. Here for Poisson random variable, e of x is lambda. And we said lambda was 4. So e of x is 4. That's the final answer. Okay, okay, so that's also easy. Next, example 6.28. If x is the amount of soda in ounces per cup, dispensed by a dispensing machine, then f of x is equal to 1 for 6.5 less than x less than 7.5, and 0 elsewhere. Okay, so x is the amount of soda in ounces per cup dispensed by a dispensing machine. Then, if x is strictly between 6.5 and 7.5 ounces per cup, the probability of that many ounces per cup in the can of soda that the machine dispenses is 1. Okay? So the PDF, which is this, the PDF of x, the PDF of the random variable x, f of x, shows x is a uniform random variable with parameter alpha equals 6.5 and beta equals 7.5. Right? This is the value of alpha, that's the value of beta. Okay, it's a uniform random variable because it just has the same value 1 in that whole interval. Right? It's a continuous uniform random variable also, obviously, because x is changing continuously, it's not a discrete random variable. Therefore, so the key here is to identify that x is a uniform random variable with parameter lambda alpha equals 6.5 and beta equals 7.5. Therefore, the expectation of x is alpha plus beta over 2. And that's equal to 6.5 plus 7.5 divided by 2. You could just memorize these formulas, right? The first one, for binomial random variable, e of x is equal to n times p. For Poisson random variable, e of x is equal to lambda, where lambda is the parameter. And here, for a uniform random variable with parameters alpha equals alpha and beta, with parameters alpha and beta, e of x is alpha plus beta over 2. So here alpha is 6.5, beta is 7.5. So e of x is 6.5 plus 7.5 over 2. That's equal to 14 over 2, which is 7. Okay? And so for each of these 3 previous problems, including this one, the problem basically boiled down to knowing what type of random variable you have, and then what the formula is for the expected value of that type of random variable, and just plugging in the values given in the problem. Okay? Okay, and now example 6.29, another example of calculating an expected value of a certain type of random variable. Right, each type of random variable has its own formula for expected value. So here's the example 6.29. If the length of time if the length of phone calls in minutes arriving at a certain switch at a certain switchboard is a random variable x with probability density function PDF. F of x is equal to 1/5 e to the negative x over 5 for positive x, x greater than 0, and 0 for x, all other values of x, x less than or equal to 0. What is the expected length per call? Okay, so the solution to example 6.29 is we're going to let x, right? X's are exponential random variable. So x is an exponential distributed with parameter theta equals 5. Okay, so we get the value of the parameter from here, right? And we see it's an exponential function. It's an exponential random variable from the definition of the PDF f of x. And so therefore, e of x is equal to theta, which is 5. And that is the expected length of individual calls in Okay? So here e of x is 5. The expected length of individual calls in minutes, okay? So we established a few things. One, we established x is an exponential random variable. 2, we established that theta for that exponential random variable is 5. And so then 3, we knew that e of x of an exponential random variable is theta. So those 3 things you need to know for example 6.29. Okay? So we found that, then we found that, and we used that, and then we got the answer. Right? And we got the exponential random variable by how the PDF was defined. Right? And here's our theta. Here's our theta here and here. 5. Okay, so the homework for 6.8. This is for 6.8. The homework for 6.8 is pages 215 to 217. Exercises numbers 1, 2, 3, 4, 5, and 10. Okay, so that's the homework for 6.8. Okay. Okay, let's keep going. Okay, so now we're up to 6.9, which is standardized random variables. Okay, so 6.9.1 is related theorems. Okay, and so theorem 6.8 there in section 6.9.1 in 6.9 is let x be a random variable with mean mu and standard deviation sigma. If y is equal to x minus mu over sigma, then e of y, the expected value of y is 0, and the variance of y is 1. Okay, so if x is a random variable with mean mu and standard deviation sigma, let x be a random variable with mean mu and standard deviation sigma. If y is equal to x minus mu over sigma, then e of y is 0 and the variance of y is 1. So the proof of theorem 6.8, proof of that theorem, is, well, e of y, which we want to show is 0, is equal to e of x minus mu over sigma, because we defined y to equal x minus mu over sigma. That's y, that's x minus mu over sigma, we can just substitute. That's equal to 1 over sigma times e of x minus mu. Sigma is a constant, 1 over sigma is a constant, and so you can just move the constant out of the expected value, so it's 1 over sigma times e of x minus mu. That's equal to 1 over sigma times e of x minus mu, right? And so now e of x minus mu is e of x minus e of mu, right? So instead of saying e of x minus mu, it's e of x minus e of mu, but mu is a constant, and so e of a constant is a constant, and so e of mu is mu, and so this is e of x minus mu there, times 1 over sigma, and to the left. And so that's just 1 over mu times mu minus mu, and that's 0. E of x is mu, so 1 over mu times 1 over sigma times e of x minus the same thing is 0. And so we just showed that e of y is equal to 0. And now the variance of y, which I'm going to move further to the left so I have room. The variance of y, again, is equal to the variance of x minus mu over sigma, because we defined y as equaling to x minus mu over sigma, so that's by substitution. This is 1 over sigma squared of the variance of x minus mu. Okay? And then this is equal to 1 over sigma squared of the variance of x. We can move, adding a minus mu here doesn't change the value of the variance of x. And so this is equal to, well, the variance of x is sigma squared, and then you're dividing it by sigma squared. So sigma squared divided by sigma squared is equal to 1. And so the variance of y is equal to 1. And that's the proof of the second part. So we showed that e of y is 0, check, and the variance of y is 1, check. We showed both those things. Okay, and so we proved 6.8, theorem 6.8 here. Okay. A random variable with mean equal to 0 and variance equal to 1 is in standard form. The random variable x minus mu over sigma, therefore is in standard form. And is called the standardized random variable. Corresponding to the random variable x. Okay, so a random variable with mean equal to 0 and variance equal to 1 is in standard form. The random variable x minus mu over sigma therefore is in standard form because we showed its mean was 0 and variance was 1 in the last theorem. So therefore x minus mu over sigma is in standard form, and it's called the standardized random variable corresponding to the random variable x. Okay, so we let y equal x minus mu over sigma. Y would be the standardized random variable corresponding to the random variable x. Okay, and the standardized normal random variable is a standard normal random variable. So the standardized normal random variable is a standard normal random variable. Okay. Theorem 6.9. So that theorem says let x be a random variable whose distribution is normal meaning, right, its mean is 0 and its variance is 1, with mean mu and variance sigma squared. Let standard form is when the mean is 0 and variance is 1. Okay, so the distribution is this is normal distribution. Okay, and so then let z equal to x minus mu over sigma. Z is standard normal. Okay. Okay, so now if you have your random variable whose distribution normal x, and let z equal x minus mu over sigma, we showed that the mean is 0 and the variance is 1. And so now z has to be its standard normal. Okay, so that's theorem 6.9. Okay. Okay. Okay, so 6.9.2 is computing probabilities for the normal random variable. Okay, so Theorem 6.9 allows us to use Table 3 in Appendix C, okay, of this book to compute probabilities for normal random variables. Okay, so you refer to the table to find the probabilities for a normal random variable, and so you reduce your problem so that by finding the value of values of probabilities on this table in the book, that will give you the answer to your problem. Okay, so if we let x equal a normal random variable with mean equal to mu and variance equal to sigma squared, to find the probability that a is less than x less than b, use theorem 6.8 to write the probability that a is less than x less than b is equal to the probability that a minus mu over sigma is less than x minus mu over sigma, which is less than b minus mu over sigma. That's equal to the probability that a minus mu over sigma is less than z, which is less than b minus mu over sigma. Okay, well, z is x minus mu over sigma, and so by our previous theorem, z is now a standard normal variable, and so z is standard normal by our previous theorem, and that implies, because z is x minus mu over sigma, and that implies that we can use Table 3 in Appendix C to find the desired probability. Okay. Okay, so by using the table, we can know probabilities for a standard normal variable z, and then now just use it to find that probability, and then you found the original probability. Okay. Okay, so in the next example, I'll illustrate how that's done. So that's this example. Okay, so example 6.31, let x be normal with mean equal to 1 and variance equal to 4. Find the probability that 2 is less than x less than 3. So the solution is that the probability that 2 is less than x less than 3 is equal to the probability that 2 minus mu over sigma is less than x minus mu over sigma is less than 3 minus mu over sigma. That's directly from the previous board. And so this is equal to the probability by plugging in the mean, which is mu, right, and the variance, which is sigma squared. So if sigma squared is 4, that implies sigma is 2, right? So sigma is 2. So this is the probability that 2 minus 1 over 2 is less than x, which is less than z. Z is x minus mu over sigma. That's less than 3 minus 1 over 2. And so that's equal to the probability that 1/2 is less than z, less than 1. And you can use the table in the book, table 3 in appendix C, to find that that probability is equal to 0.1498. Okay, and then that's the answer. So the probability that 2 is less than x less than 3 for this example is equal to 0.1498. Okay, and so the homework for this section is pages 219 to 220. Exercises, numbers 1 and 3. Okay, and so the homework for 6.9 6.9 is page 219 to 220, exercises 1 and 3. Okay, and so we're going to stop there, and I'll see you next time.